Welcome back to the show that tells you you are a quantum computer with free will. But hey, I'm just one guy, so I want to hear what you have to say. Please leave a comment below, like the video, subscribe to the channel, and let's get this discussion started.
Join me deep inside the mystery of numbers. Come and have a metaphysical view. See how concepts become objects and then become qualia. Join us for an episode of Quantum Consciousness.
Hey there, welcome back to Quantum Consciousness. My name is Justin Riddle, and this is episode 6, in which we will be talking about quantum computers. So in our previous episodes, we talked about Roger Penrose's three-world model, consisting of a physical world, a mental world, and a platonic world. Physical world of the observable universe around us, the mental world of our thoughts and feelings, and the platonic world of concepts, mathematics, and meaning. Then I told you about digital computers and how digital computers really highlight the measurement principle in the physical world, defined by bits, which can either be a 0 or a 1, here or there, and really are the definition of what is physical. Every computer has a central processing unit resembling a mental world, and software which implements specific concepts, mathematical principles, and runs them out in the digital computer, approximating the platonic world. And the subject of today is to talk about quantum computers and how this fits into the three-world model, and relating them to digital computers to sort of give you a sense of how these two domains interact with each other. And then we'll be looking at the future of technology, looking at historical trajectories, and thinking about what quantum computers might mean to society or to the nature of consciousness. So to launch us off into quantum computers, I'll be making the argument today that you are a quantum computer and that quantum computers really are fundamental to an understanding of cognition and consciousness, and that they share a lot of similar principles to what it means to have a mind. And we'll get into this in a second. All right, so quantum computers, they exist. You can buy one, theoretically. They cost millions of dollars. But Google's developing them. A couple private companies are developing them. And it's really here right now. And I think this is something that people don't fully appreciate. But for example, digital computers existed for many decades before they became affordable and widely used. And we're sort of at the same point in history right now in 2021 where quantum computers exist, but normal people out there in the world don't own them. And so it feels a little bit intangible. But similar to the internet and digital computers, it's almost guaranteed that these will take over the market at some point in the future. When exactly that is, I'm not totally sure. I was always overly optimistic in the past, so I have no clue. But we will talk about that a bit at the end of this video. All right, so quantum computers embody these principles of quantum mechanics that we talked about. And so really we'll be zooming into the measurement principle and the superposition principle. And these are really key to us understanding quantum computers. And then entanglement will sort of be hinted at in terms of future applications of quantum computers. But really superposition is sort of the defining principle of a quantum computer, just like measurement was really the defining principle of digital computers. And then at some future point in time, a much later video, we'll be discussing this notion of a fractal computer or some sort of higher order computational process that currently eludes modern technology. But, let it be known that quantum computers are potentially the most analogous thing to human cognition, or might be fundamental to us reverse engineering human consciousness. However, this is by no stretch of the imagination the end of technology, and there's presumably future technologies beyond quantum computers that will probably transform how we view things. And I have a few speculations on that, but first we got to digest quantum computers. So quantum computation requires a digital interface. And this is really the interaction between the physical and the mental world. And essentially, we will always need digital computation. And in a sense, quantum computation is sort of fundamental to digital computation, wherein digital computation is a subset or a reduced form of quantum computation, where you're sort of digitizing everything, measuring it to the point where there's a reduction of all quantum effects, which we discussed in the previous video. And so in quantum computers, you're really harnessing that naturally occurring superposition sort of under the hood. But nevertheless, you still need to interface digitally with the quantum computer. So digital computers will always be essential to quantum computation in that you need to sort of set up your quantum computer in a digital state, allow it to quantum compute some solution, and then you measure it again, and it reduces it back into a physical state, and that physical state can be read out digitally. So essentially, digital computers provide the input and output interface essential to running a quantum computation. So what this might look like is that you have these fragile quantum superpositions, and so we need to isolate and encapsulate that quantum system so that there's no measurement from the environment, because any sort of environmental influence can destroy the superposition and create a premature measurement of our wave function of our quantum coherent system. And so we need to have a protected period of time where the quantum computer can internally process this information, this quantum computation, and then after a set amount of time, we can provide our measurement process and actually reduce that wave function away and get out the output of that quantum computation. So it's sort of a cyclical process of quantum computing, digitization and measurement, and then preparing the next quantum system to compute a new problem, and then allowing that to run and then measuring it again. And so there's this, repeated quantum phase, digitization phase, quantum phase, digitization phase. And this has theoretically been connected to biology, and we'll go into this in our conversations on biology, where if we look at a biological quantum computer, you would want to see these principles where you have moments of isolating the quantum computation to run internally in isolation from the environment, and then you want to expose it to the environment, allow inputs and outputs to be gathered and inputted, and then a return to that isolated state. All right, so really at the core of a quantum computer is quantum coherence. And quantum coherence is the ability for a wave function to encapsulate many physical objects or states. So one simple example is a superatom. So there was this experiment, and this has been run, where you take rubidium atoms, and if you supercool them near absolute zero, these atoms will coalesce into a single superatom, where now each of those atoms shares a wave function with each other, and it's as if they are just one superatom, and the single atoms are indistinguishable from each other, and theoretically and in principle, it is like inappropriate to even view them as separate atoms because their state is so interconnected. So if you ask the atom, where are you? Or, are you moving? The response of any given atom is dependent on the collective. And so there is a quantum coherence and a single wave function governing the response of any single atom. And this is really the defining element of superposition, is that you need to understand where the boundary of your quantum system is. So previously we introduced this notion of a superfluid, very similar to that superatom, where you take helium atoms, you cool them down to a very low level, and then they coalesce into a single fluid or a superfluid that is governed by a single wave function, and the helium atoms are no longer distinguishable. And so the superfluid displays very interesting properties. One of them is zero entropy. So entropy is a measurement of chaos, and essentially there is zero chaos within this system. So they are perfectly intermeshed, and there's a single wave function or a single process guiding all of the atoms, all of the physical matter within the wave function is behaving as if it was one thing. And this is a property of zero entropy. Now, at the same time, it also has entropy. And so there's sort of this weird duality going on within superfluids and superconductors, superatoms, what have you, where they have properties of being zero entropy and having this perfect wave function or unity across them all. But then at other times they'll display properties of being separate from each other. So there's definitely some weirdness, and I don't fully understand all these details. But in a quantum computer, the goal of the quantum computer is to create a very large single wave function. And so when we're talking about these different atoms, we can view these different atoms, for example, as being bits of information or having the capacity to store bits of information. So instead of a bit, we refer to these as qubits or quantum bits. And so these qubits could be anything in nature. They could be an atom where you have a low energy ground state or a high energy state, and the high energy state is a 1 and the ground state is a 0. And so an atom could behave as a quantum bit. And so instead of being locked into the ground state or the high state, we know from science that the atom will actually evolve and be a superposition of being a probability function of I'm a little bit in state 1, a little bit in state 0. And then when you measure the bit, or you measure the atom or the quantum bit, it becomes a 0 or it becomes a 1. But when you're not looking at it, it's evolving into a probability distribution of being in both of them. And so what you can do is you can take a bunch of these atoms, and granted, it can be many different phenomena. So you could have optical systems with laser light. You could have electric flow patterns that are in superposition. So there's a bunch of different options of how you could do this. But essentially at the core of the quantum computer is that you want to create a large wave function of many of these quantum bits. So whatever medium you're using, you want multiple of these systems to be wrapped up into a single wave function, and then the computational power of your quantum computer is dependent on the number of qubits that are within the system and that have quantum coherence with each other. So the goal of making more and more powerful quantum computers is basically overcoming decoherence and that environmental destruction. And we're really trying to harness quantum coherence and creating as large of these quantum coherent qubit systems as we can. And so the power of a quantum computer is proportional to the number of quantum bits inside of it. So if we compare a digital computer to a quantum computer, the digital computer was powerful enough equal to the number of bits that it can store, for example. So you have these zeros and ones, and you want to maintain your 1 into the future and your 0 into the future, and this is that solid state that you need to create. And the power of your digital computer is the number of bits that you can have, the speed at which you can move these bits or transform these bits. And this is a linear process. So as you increase the number of bits, you increase your computational power, but it goes up linear. So I go from 10 bits to 100 bits to 1,000 bits, and the computational power scales up equal to how many bits I have. Now, what's very wild and amazing about quantum computers is that the computational power exponentially grows with your number of quantum bits. And so how you measure the power of a quantum computer is essentially how many states the quantum computer could be in. So if you have 2 quantum bits, you have a 0 and a 1 and a 0 and a 1, and then you have 2 times 2, you have 4 possible states that you could be in. 1 1 0 1 1 0 0 0. But once you have 3 bits, now you don't just have 6 states, but you have 8. And then you add another one, and now you have 16 possible states, and then 32, and then 64, and then 128. And so this scales up exponentially, where it's 2 to the number of quantum bits, as opposed to just 2 times the number of bits in a digital computer. And so this exponential increase in processing power is really remarkable and totally mind-blowing. And I will come back to this in a moment, where I try to really make this apparent to you, how much stronger and how much more powerful quantum computers can be relative to digital computers. Like, if we're viewing the strength of our computation digitally versus quantum, versus in a quantum computer, the scales are enormous, and it really gets a bit wacky. So I'll come back to that in a second. But and then in a future episode, I'll talk to you about biology. And one of the questions here is, could we have quantum computers in our biology? And once again, the big challenge is quantum coherence. So you need to be able to preserve these very fragile states. And so there's people working on this and looking at biological systems and trying to study, are there tricks that biology has pulled off in order to create quantum coherence across larger and larger domains? Because what would be really striking is that if we have been measuring the strength of the brain, for example, in a linear fashion, if there is any capacity for quantum computation, much smaller quantum computers can drastically outperform the biggest, most powerful digital computer that we could construct. It takes a very small quantum computer to just absolutely destroy a super powerful mega digital computer. So the implications of this are massive. And then I want to also point out this notion of universal quantum simulation. And this is the idea that because quantum computers are made out of the basic units of reality, right? Quantum computation basically occurs for free and essentially is just naturally occurring. So quantum computation just sort of happens, and we can rig up quantum systems to evolve in certain ways, and we can kind of shape algorithms out of this naturally occurring process. But really the challenge is creating quantum coherence. And then once we have that, we can just shape the evolution of these quantum computers through time, and that essentially is the algorithm that we end up running. But it is a naturally occurring process, and so universal quantum simulation refers to the fact that if we want to simulate the interaction of, let's say, 2 proteins or a couple atoms, we can, in principle, simulate naturally occurring phenomenon with the quantum computer. And the quantum computer is indistinguishable from that naturally occurring process. So in a sense, reality and simulation kind of fall apart. And this is where I personally have qualms with the whole simulation theory of the universe, is really like when people talk about simulation theory, I think they're referring to digital computation, because in a quantum computer, the ability to simulate or to reenact a naturally occurring phenomena is in some sense indistinguishable from that naturally occurring phenomena, because you're making it up out of these naturally occurring atoms. And so you can recreate directly what is happening in your simulation. What's important to note is that it's still a probabilistic process. So when you measure a quantum computer, it gives you a random output based on that probability distribution, but you can simulate this multiple times and regenerate that probability distribution again and again. And then every time you measure it, you're kind of learning about what that distribution looks like. So in essence, the invention of quantum computers will radically transform biology, because we'll then be able to, in a quantum computer, simulate protein interactions, simulate atomic interactions, and chemical reactions in a one-to-one manner. So instead of like building all this mathematical models upon models to simulate, femtoseconds or picoseconds of time, we'll just run the chemical reaction in this like simulation, and it'll be the equivalent of that in sort of an information processing sense. So this is a very cool idea, and I put this within the three-world model as sort of approaching the Platonic, because similar to software and universal Turing machines, there is a connection here where you're essentially simulating reality as it is. And so there is kind of like mathematical truth or conceptual truth built into your simulation somewhat inherently, because you can have multiple quantum computers simulate the exact same thing. And sure, there's going to be a probabilistic output at the end, but there's still sort of this like fundamental conceptual framework that your quantum computer is operating within, and you can basically run multiple quantum computers simulating the same event, if you will. And yeah, so that sort of wraps up my introduction to quantum computers, but I really want to now emphasize this difference between what is computable by a digital computer versus what is computable by a quantum computer. So to highlight this difference in runtimes between digital and quantum computers, I'll give the example of Euler's path. And this is a very early question on how digital computers solve things and how many steps you need to take to get the solution to a problem. And so the question of Euler's path is, if I have a bunch of different islands and bridges, can I visit every single island, crossing each bridge only once and never crossing any of them twice? And so if you have an example where, let's say, you have 4 islands and 7 bridges, the question is, can you pull this off? And the solution is that the path exists if every single node has an even number of bridges, and then the start and the stop node could have an even or odd number. And so this is kind of a shockingly simple answer to what seems like a really complex problem, but the runtime of this algorithm is proportional to the number of edges and the number of nodes within this graph. So the runtime is basically, I go to each of these different nodes, these different islands, and I count the number of bridges, and I just check, I can have 2 odd ones and every other one has to be even. And then once I've gone through every single island, I now have my answer, right? So if I were to add more and more islands and more bridges, there's sort of a linear increase as I get bigger, where now I just have to go check more and more islands. So I'm going to contrast that Euler's path by what's called Rudrada's path. So let's say I have a chessboard, and the standard chessboard is 8 by 8, But let's just say, for the sake of argument, I could scale it up as big as I want it to be, right? And the question is that if I take the night, which can go 2 down and 1 to the right, or 2 down and 1 to the left, or 2 to the left and then up or down 1, I'll put a graphic here to illustrate that. The question is, can I go to every single location on the board exactly one time, not overlapping? So I can't go back to the same location ever, but can I cover the space on the chessboard? And so how do you solve this one? Well, you essentially need to walk down every possible path. So for simplicity's sake, let's just say there's only 2 options, when in reality, there are much more options. So let's say I go down my 2 paths, and then from each of those, I can go down 2 more paths, and then each of those, I can go down 2 more paths, and essentially, I go up to the number of squares on the board, right? So this is 2 to the power of v, where v is the number of squares on the chessboard. And then once I've gone down all these paths, I will know whether or not I have found a solution, right? So by the time I've run all possible paths, I either find it or I say, nope, I tried every path, there's no solution to this, right? So if we compare these 2 algorithms, and a simple way of looking at this is, let's just say one algorithm runs in v squared time and another algorithm runs in 2 to the v time. So this is a polynomial algorithm versus a exponential algorithm. And as I increase the number of nodes, let's say at level 1, I have 1 in the polynomial and 2 in the exponential. With 2 as the input, I have 4 in the polynomial and 4 in the exponential. So they're doing pretty similar. And then when I hit 3, it's 9 in polynomial and 8 in the exponential. At 4, I have 16 in the polynomial and 16 in the exponential. I hit 5, and it's 25 in the polynomial and 32 in the exponential. They're pretty similar, right? But now let's jump up to 30. Now I have 900 in the polynomial, and I have 1,073,741,824 in the exponential. And once I hit 40, I have as many possible paths as there are atoms in the universe, right? So once you hit 40, you really hit these astronomically wild numbers, versus 40 in a polynomial sense isn't really that high at all. And so the real question here is, can quantum computers run these exponentially large algorithms? And so if you're a computer programmer out there, you're acutely aware of this. But in digital computation, we have to be really careful not to have exponentially large problems. And there's a lot of clever tactics that you have to employ in order to not hit these exponential runtimes, because digital computers will just flat out run out of time. And if you give it an exponential problem of sufficient complexity, your computer's not going to finish running until the end of the universe, right? So this is actually a really big challenge in digital computation. Is, there's so many instances where we want to search all possible solutions, but you can't genuinely go search all possible solutions. We have to kind of hack them down artificially and wiggle our way into finding a suboptimal solution, but still decent solution. And so in digital computers, we avoid exponentially hard problems, even though they are very naturally occurring and happen very easily. It's easy to write bad computer code that will take an infinite amount, or not infinite, but a really long amount of time to run. And so it's not even worth running it, because you'll never get an answer before you die, right? So one of the questions with quantum computers is that these quantum bits scale up exponentially. And so the idea is, could a quantum computer simulate the evolution through a search space such that you can search an exponential number of options of paths in a linear amount of time, in this polynomial fast amount of time. So let's say my quantum computer is made up of 40 quantum bits. I started off in this state, and then the superposition evolves and keeps blowing up into all these more and more different possible states. The growth of the superposition occurs at an exponential rate. So every time it evolves, it is exponentially growing. And so the idea here is that while a digital computer will have to walk down every single path manually and laboriously checking every single possibility, the quantum computer might, in a natural way, evolve down all possible futures simultaneously. And then when it hits the answer or that, optimal solution, then it converges on that optimal solution. And the runtime to get there is equivalent to just walking down the proper path. So this is kind of wild, right? You're walking down every path simultaneously such that when you get to the right solution, it's the equivalent of having always made the correct decision in going to find your answer. So this is truly mind-numbing in that you could maybe do these exponential searches in a normal time frame and potentially even faster than digital computers could even walk down the proper solution, right? The catch is, it's a probabilistic process. So when you measure your quantum computer, at the end of the computation, you'll have a probability distribution and you might get some spurious, suboptimal, or incorrect answers. So you just run your quantum computer a few times and then you pick the one that showed up the most often. And also, it's typically easier to check if you got the right answer than to get the right answer, right? So it's easy to check. It's hard to just jump to what the correct answer is. But you can, once you have it, you can check if it's real or not. So this is really one of the major potential future applications of quantum computers is running these exponentially large algorithms in linear time. And so the computational power that we might be able to achieve is really mind-numbing, right? So if you think about the brain, there's, I'm going to get the numbers wrong, but there's like 200 billion neurons, and then there's like, a trillion connections between those. And so you go, wow, maybe like the computational power of the brain is equivalent to the number of connections between neurons. And then it can run, let's be generous and say there's like 100 computations per second at a trillion synapses, right? It seems like a large number and it seems like a lot of computational power, but if you could get a quantum computer that has, let's say 200 or, 1,000 quantum bits, you now have 2 to the 1,000th power computational, power potentially. And that just blows anything, out of the water. So very small quantum computers, once again, can completely destroy the computational power of large digital computers. And if there is quantum computation going on in the human brain, then our estimates of computational power of the human mind is totally wrong. It's so far incorrect that we can't even wrap our heads around how incorrect and how trivially small our estimates have been relative to any form of quantum computational power going on in the brain. So a couple things to spin off of this conclusion here is that this is only scratching the surface of potential applications of quantum technology. So there's notions of cryptography, where because of entanglement, you can have these unique, non-clonable quantum systems. And so this might serve as a form of perfect encryption where it cannot be hacked, maybe by definition. Counterfactual computation, where you can check what would have happened if I were to do this, but then not actually do that. So there's ways to simulate possible events without actually disturbing the thing that you want to go and probe. And we'll talk about this a little bit more in the future. Potential teleportation, where you could have instantaneous transfer of information across space. And this is somewhat debated, but yeah, you could potentially have these like massive speed ups to information transfer. And then there's also a notion of time reversibility in quantum technology, but once again, I don't think we even know, I don't think we really even know what that would look like at this point. To connect quantum computers back up to the three-world model and back up to the human mind, the defining feature of a quantum computer is quantum coherence. And the idea of our mental world is that the defining thing about our consciousness is that we feel like we are a self. I identify as Justin Riddle. I have an I and a me and a sense of self. And quantum coherence could be the way that you're able to create single entities out of a physically distributed system, right? So it really creates unity and it creates entities. So in a digital computer, there is no single thing. There is no, it's just a bunch of sub-processes and you can just divide it up as much as you want. But in a quantum computer, you can't divide it. You want to have one giant quantum computer. And so the human mind, the sense of self that we have, and this is purely speculative, but there would be a technological advantage to having a single mind, to having a single giant quantum computer, because it would be the most powerful, right? It would have the most computational power to pump all of your information into a single wave function, into a single quantum coherent system. And so evolution would then tend towards the creation of large macro entities, and they might have a sense of self because they are one thing. They have a single wave function governing the whole quantum computer. And so you would see evolution selecting for minds or selecting for something like the human mind or like a mind. So I think this is a really powerful, interesting thing that falls out of quantum computers, where in digital computers, there's no point of having a human mind. There's no point of creating this theater show of being a self. And so there's all these like hoops you have to jump through to like say, oh, well, why would the brain create this fake sense of self? What's the point of that? And it's hard to think of one. But from a technological standpoint, within a realm where quantum computers exist, oh yeah, you would want to create one giant mega computer within your biology because it can do these massive computational processes. And then I think some fallout of this is that, your mind and your thoughts and your feelings are computations. They're quantum computations that are simulating and processing information into the future and selecting actions and outputs and integrating all this information. And the computational power is just unfathomable given our modern technology. It just totally outperforms any digital computation you've ever seen. And so, we're unable to even really grapple with these notions of mega quantum computers and what that might look like. So, yeah, I think to me that is super cool and very inspiring. All right, so what about building quantum computers? So, yeah, this is, the part of the speculative, portion of this video, but I wonder if we will be able to build large quantum computers and maybe reverse engineer minds before we really understand what we're doing. And this is somewhat an ethical question, but digital computers they're not really made out of the substrate of reality. They're just a bunch of like electrons in clouds, and we're like creating these solid states. But once we start making quantum computers out of raw elements of matter, we're going to be creating these macro systems. And then, who knows if they start having more naturalistic looking behaviors, and this kind of like a ethical question of what this might mean. So yeah, I think we're looking at a near future where we start making things that have so much more computational power than we're used to seeing, that it might have more naturalistically occurring behaviors, and I think it's an important question to think about. Are these potentially conscious beings or not? Yeah. So we'll return to this more, but that's kind of a teaser of this way of thinking. And I think this also has implications into how we think about our place in all of this. So from looking at mainstream movies and film and television, most movies just talk about digital computers. And I think it's very common to then get this Terminator scenario where, digital computers are like, we must run efficiently. Everything is about the binary, and the zeros must stay zeros, and the ones must stay ones. And this messy, organic human life defies the zeros and the ones, and it just will flip between zeros and ones chaotically. What a shame. And so, in Terminator and iRobot and all these movies, it's like, we must kill all the humans because they're too messy and organic and they're not efficient. And so the value structure assembled along digital computers is based on maintaining the zeros and ones in this sense of like crystalline order into the future, and reducing entropy, and humans are too entropic, and so they must be eliminated. But I think in an era of quantum computers, what does it mean to have optimal functioning? Yeah, maybe quantum coherence is valued, so you want to create larger and larger quantum coherent systems. But it's a little bit less clear what it means to be an efficient quantum computer, because it is sort of this naturally occurring process. Maybe you want to pump as much different, a diversity of information into a single quantum computer, and then it makes a much more colorful computation come out in some way, So this is a little bit vague, but it's kind of just saying like, what will the value system or the efficiencies look like within the domain of quantum computers, and then questioning this narrative of, chaos is bad, right? Because in a quantum computer, maybe a little bit of chaos is a good thing. Who knows? It just kind of like defies that, that sense of hyper efficiency. And another cool idea that I think comes out of this is this idea of making larger and larger quantum computers. And there's this really great short story about this by Isaac Asimov called The Last Question. And in The Last Question, these future humans are making larger and larger and larger quantum computers, or I'm interpreting them to be quantum computers. But the goal is you want to have as big of a quantum computer as you can because it can compute the most information possible. And so you're just making a larger and a larger and a larger quantum computer. And then in that short story, eventually the entire universe is wrapped up into a single quantum computer, a single computational process. And then who knows what happens once the whole universe is enveloped in this single giant quantum computer. So, I mean, who knows if that is like at all a feasible future, but fun to think about nonetheless. All right, so I'm going to end with a discussion about The Singularity is Near by Ray Kurzweil. And this was a really impactful book in my past, which really inspired me at a young age to really dive into this. I remember coming home from my first year of undergraduate and just wanting to be a cyborg and wanting to merge with computers. And thinking back, it was kind of silly and based in a very digital way of thinking. But at the same time, I think Ray Kurzweil has really noticed some really powerful historical trends. And I want to just kind of convey his discussion of this. So there's something called Moore's Law, and Moore's Law is basically stating that there's an exponential growth in computational power over time. So every, I don't remember the details about how fast this happens, but let's say every year and a half, we double the number of bits that we can fit onto, a small piece of matter, or like a small, square centimeter of matter. How many bits can we fit into there? And there's this growth where every year and a half it doubles, and it doubles, and it doubles, and it doubles. And this is exponential. So it has all those properties of growth that we were talking about previously. And what is mind-blowing is that, why should it keep going? And every year, people come out and say, Moore's Law is over. There's no way that it's going to keep going. And it's really just human efficiency or human creativity that is pushing Moore's Law forward. And so it's kind of this mind-boggling historical observation, and it's just based in human creativity to make the next most amazing device. But what we're running into right now is that digital computers are sort of maxing out at their maximum efficiency. And I discussed this previously, but we might be hitting a digital brick wall where our computers can't get any better. Digital computers. And so the question is, are we due for quantum computation to enter the scene and to pick up Moore's Law where it's leaving off with digital computers? And we'll keep seeing exponential growth in computational power, but it's only going to be enabled through quantum computation. And quantum computation seems to be here, and digital computers seem to be leveling out. And so, wow, kind of remarkable that they're coming on the scene right when we're starting to need them to keep up this Moore's Law trend. Now, Ray Kurzweil extends this exponential growth in technology into history. And so one thing he did was he took all these major scientific contributors and asked them, what were the major events in human history, in the history of the universe, and he put them on a time graph. So I'm going to read a couple of them here, but life, eukaryotic cells, the Cambrian explosion, reptiles, primates, mammals, hominids, human ancestors walk upright, spoken language, Homo sapiens, art, agriculture, writing, city-states, industrial revolution, printing, electricity, computer technology, the internet. And all of these different major events fit an exponential trend. And so the shocker here is that we might be, as human beings, fitting into a Moore's Law at the scale of the universe, where technology is evolving at an exponential rate, and we happen to show up here on the planet right when there's this massive launch off in technology, where these revolutions, which were taking on the order of millions and billions of years in the past, are now happening on the order of decades. And so if we're having revolutions on the order of decades and centuries, what does that mean for the very near future? And so Ray Kurzweil says that the singularity is near, meaning that our computer technology is going to turn into higher and higher levels of technology, and it's going to start undergoing these rapid increases at an exponential rate. And then the kicker is that this might happen at the rate of, it used to take 1 million years for evolution to occur. Then it took 1,000, then it took 10, then it took a year, and then potentially it'll take a degree of hours, right? So we invent the internet, and then an hour later we invent the next technology after it. And then it'll take an order of minutes and then seconds. And so the singularity is this idea that there is a technological exponential growth that's going to peak in our near future, and we'll see a level of technological growth happening on such a fast time scale that Ray Kurzweil argues that we'll have to merge with the technology to be able to even keep up with it. And it's speculation what that might look like or whether or not this is really going to happen. But boy, is it fun to think about. Alrighty, so yeah, I'll leave you with this, but I think it's really cool to think about the past. We come from chaos, we come from disorder, and if you look around you, the universe is getting increasingly organized and increasingly more full of information processing, and it's really exciting to be alive right now and to think about what might be coming just down the road in our future. Alrighty, signing off. I will talk to you all later.